Hi, I'm Ben-Yaakov. This presentation is entitled Linearization of Multivariable Function and SPI. As a way of introduction, let us consider this schematics in PSPIs, which I'm showing here. Let's forget about these two sources. These are transient sources, sinusoidal sources for transient analysis, and we are now concerned with AC analysis. So these will be disregarded. And we have here two AC sources, one 10 volt, the other one is 20 volt. There is a DC source, 1 volt, and then another one, 2 volts, inserted with the AC sources. And these are fed to a multiplier. This is an analog multiplier. It's an ABM, analog behavioral model, and there is an output. So I'm running this circuit over the frequency range of 10 hertz to say 1 kilohertz. It doesn't matter really for the purpose that I'm demonstrating here, but still we need to specify some frequency range. What we are getting here is 40 volt. This is a AC output, steady state, AC analysis, and we got 40 volt. And the question is, why is it 40 volt? We have here 20 volts, we have here 10 volts, we have 1 volt here, 2 volts here, so how come we got 40 volts? In this presentation, I'm going to explain how this number is obtained and what is behind it. Let me first of all talk a little bit about the meaning of linearization in a way of demonstration by a small circuit here, which you can say it's an analog attenuator. We have a diode, a series resistor which is connected to a DC, so the diode is biased to a given point, say let's say this point. And there is an AC source coupled via a capacitor, and there is the output, also capacitor coupled. By changing the DC, you can move on the VI curve of the diode, and the local slope, which represent the actually 1 over resistance, and therefore the resistance will be changing, so that you got a divider here which depends on the value of this DC. So by this DC you can control the attenuation of this circuit. Now we can analyze this circuit by say SPICE, by AC analysis, and this will be done after linearization. And here is the linearized circuit. In this circuit, the diode is replaced by a linear resistor. There's no DC here, it's been subtracted. And we have only the AC source and all the other components. This is now a linear circuit, and it can be analyzed by phasor equation. Say the impedance of the capacitor will be 1 over j omega c. And this will be solved by SPICE, and we can get an output which will be of course correct for a certain DC level which has set this RE, this equivalent small signal resistance. So the steps for running an AC analysis or for the linear circuit to work is first of all to find the operating point, and then to take the derivative here, which is the slope, which is the small signal local behavior of the function, and replace the nonlinear element with this linear, local linear element. So when we are running SPICE in AC analysis, there are many steps that are taking place. Most of them are transparent to the user. We feed in through the schematic capture the circuit, and then SPICE will calculate the operating point. It will linearize the circuit. It will solve the circuit by linear phasor calculation, and then it will store all the results in this .dat file, which is then available for display by probe. When we are talking about linearization by SPICE, there are actually two types of linearization that can take place. One is using a built-in native models which are available for devices which are recognized by PSpice. For example, a diode is a native element, and Spice has a built-in template of this linear representation of this diode at a given operating point. And after finding the operating point, it'll calculate the resistance and the capacitance. There's a nonlinear differential equation, as a matter of fact, that has to be solved in order to get the local capacitance under specific bias conditions. So these are the native elements that Spice has already a template for the linear equivalent circuit. But in the case that it is non-native element, then Spice has to do the linearization itself. And we are going to talk about it in a minute. Before that, let's see how are we going to do it, say manually. If we have a problem like this, how can we linearize a circuit when, of course, the nonlinear element is given? So here is an example. We have a DC, we have an AC, we have a resistor, and there is a nonlinear element which I have defined here as the current of this element is equal to some constant times volt squared. The VE is the voltage across this element. So it's a nonlinear element. It's nonlinear because there is a multiplication here of two independent variables. So what I want to do, I like to replace this by this circuit in which this will be linear. It could be a resistor and it could be a dependent source. A dependent source is a linear element. So here what I'm going to do. First of all, I have to find out the operating point. For that, I'm disregarding the AC, and I have here now a DC circuit. Let me first of all talk a little bit about notation. Capital and small e will be the total value, small letter and a small subscript will be the AC component, and a capital letter and a capital subscript will be the DC component. So here we have only DC component. So this is the current DC, this is the voltage, and we can now solve this equation by, say, KVL. Here we have VDC minus the drop on this resistor is equal to VE, and we know the expression for IE, that's the expression, and then I can plug it in, and I'm getting a second order equation, and this is the solution. So this is sort of representing the function, and I've found the operating point. This is the voltage, and of course, once I know the voltage, I plug it in, I get the current. This is the operating point. So the next thing to do now is to take the derivative here in order to get the slope here. And for that, we have to take the derivative of this function, which turns out to be this value, 2 times Ke times Ve. And this is in fact, because this is a ratio between changes in current over voltage, this is in fact Gm, or 1 over Re. So we can say, by multiplying here this dVe here, that we have the small change in I is equal to some constant times the small change in Ve, or in terms of small signal, we say that the AC current will be equal to Gm times the AC voltage. And knowing now Gm, we got it through this derivative, I can now represent this circuit by a linear circuit, which will be either Gm VE or Re when Re is 1 over Gm. These are two equivalent, two ways to do it. Once I have it, I can, of course, find out what is this voltage here by just a voltage divider, knowing the input voltage. So this is how I do it sort of manually in an analytical way. There is a way to do it graphically. I'm representing it here only because it sort of brings in an insight into what is really happening, and that is you can draw the function of the nonlinear element, here it is, and then draw the slope of the resistor starting from VDC. This is the slope of this resistor. The idea is that the voltage drop across this resistor plus this element is equal to VDC. So the voltage drop of this element plus the voltage drop on the resistor is VDC. This is the intersection in which, of course, the two have the same current. So this is the solution here. And if you now draw a sort of a line here, slope that touches this curve here, then of course you can get the GM, which is the tangent alpha. This is the angle here, alpha. So this is just an insight of what's really happening. The question is, of course, how is SPICE taking care of all this? So to do that, I've drawn here the circuit that we've been talking about in the SPICE schematics. We have a DC. All have to be, of course, specified. All the numbers have to be specified because SPICE is the numerical calculator, and it's doing numerical calculations, so everything has to be numerical. So we have a voltage, 2 volts. We have a AC, 20 volt AC, 1K resistor. And then we have this element, which I've chosen for representing the product of VE. I've dropped the K here. So this is an ABM with the current source at the output, ABMI, analog behavioral model, which has here an expression which defines the value of this current. So this current is equal to VE times VE, VE squared, VE being the voltage here is reference to ground. This point is ground. So the first thing would be to find the operating point. And as I've said, SPICE is capable of calculating this circuit, finding the current and the voltages of a nonlinear circuit. This will be a DC circuit because this will be shorted or disregarded, and the solution will be the operating point. Next, there's a need to take the derivative of this thing. Now, obviously, it has to be a numerical derivative. So how do we do that? So here is a function that we have to take the derivative of. Now replace it by delta. That is this will be a delta of the function, small change in the function, divided by the small change of the independent variable, x. Now, to get this delta, what we do, we take the function, we add some epsilon to this independent variable around the operating point. This is the operating point that we have found in the DC. And subtract from it the function without this epsilon and divide the whole thing by epsilon. So this is the delta fx and this is the delta x, it's epsilon, which is now the derivative. So the next thing would be to do it on the actual function that we have. Here is the function which is v squared. We add to x and epsilon, and this would be by adding to VE and epsilon, and now this is squared, which comes to be v squared 2v epsilon plus epsilon squared. Now epsilon being a very small number, so theoretically in a derivative you assume this epsilon goes to 0 and therefore this actually becomes 0, or in the case of SPICE, it's going to be a very, very small number. So we are going to neglect it. So this is the function after adding the epsilon to it. And to get the delta fx, we have to subtract the function without the epsilon, divided by the epsilon, and lo and behold, we got this value, which is 2VE as we got it before, which is GM. So this is done now in a numerical way. That is, what SPICE will do, it will first calculate, of course, the operating point and get the current, and then it'll add to E some epsilon and calculate again the current, take the difference between the extended value with the epsilon to the original value and divide it by this epsilon, and this will be the number that is going to be put here as a linear dependent source. And now this circuit is going to be solved by a phasor calculation. Now here we don't have any reactive elements, but in general you might have capacitor, inductors, etc. But the calculation is algebraic, no differential equation involved because it's a steady state linear circuit in a steady state. Okay, we understand all this. So why do we get here 40 volts? There's 10 volts here, 20 volts here. Why is it 40 volts? So let's now reconstruct the calculation that was done by SPICE for this particular case. In order to do that, we have first of all to look into a more extended situation in which the function is not just for one independent variable, but a number of independent variables, a multivariable function. In this case, the derivative is defined as the differential, that is dy, the derivative of this function, if the partial derivative with respect to one of the independent variables times dx plus the partial derivative with respect to the other independent variable, etc. Of course, SPICE, being a numerical calculator, will do it in a numerical way, which means that in order to get, say, the partial derivative with respect to x, it'll take the function, add to x around the operating point some epsilon, subtract the function without the epsilon, divide by the epsilon, and this is now this coefficient. It is a number at the operating point. In a case of, say, a product, we have two variables here. It'll be the partial derivative with respect, say, to b, so it'll be the DC component or the operating point component of a times small b, like dx, operating point of b times a, and if these are voltages and the a and b, the small a and b are actually small signals, then what we get here is the DC of a times AC of b plus DC of b plus times AC of a. So this is the differential of this function. Now the problem that I've posed is indeed this case. Here we have this function. It is a times b. This is this function. Now, a0 is the DC component, and this is 1 volt. b0, this is the DC component, is 2 volt. The small signal a is 10 volt. The small signal b is 2 volt. Okay? The output is a times b. This is the function. And it has to be a times small b, b operating point times small a. So a times small b is 20. 2 is b0 times a is 10. Comes out to be 4. So this is how we got this 40 volt here. Now, so there's no question that SPICE calculation is correct. We have sort of done it ourselves, and we see that this is the number you are supposed to get. But the question is this is really the correct solution to this problem? And the answer is no. Because we have here 10 volts, 20 volts, 1 volt, and 2 volts DC. This is not a small signal situation. This is a large signal. And in fact, if I run it now in the transient analysis, time domain analysis, I'll invoke these two. The DC is the same, but I'm replacing the AC with the sinusoidal time domain sources. Here is what I'm getting. So this has nothing to do with the sinusoidal waveform. It's a distorted waveform. because they are products of these two waveforms. And therefore, the 40 volt that we got is just incorrect. It's garbage. That's what it is. To understand it better, let's go back to the example of the attenuator. Suppose we have an attenuator, and let's now put some numbers, say it's 5 volts. I'm setting this to a certain operating point. And now, and this will be the linear circuit, and now I'm going to feed in 10 kilovolt AC. If I'll feed this to SPICE, this is the linear circuit that SPICE will generate, and it will solve it. And obviously, you'll get here something like, I don't know, a couple of kilovolts or maybe hundreds of volts. But obviously, this is garbage, because if the signal is so high, this diode go into cutoff and conduction, and the whole thing will be distorted here completely. The point is that when you carry out a SPICE AC analysis and the circuit is linearized by SPICE, it is your responsibility to make sure that you are feeding signals which are compatible with the idea of a linear circuit, which is a small signal analysis around an operating point. SPICE will give you no indication that something is wrong, because for SPICE, this circuit is legal. There's nothing wrong with it. It's a circuit, there's a 10 kilovolt input, and there is an output, and that's it. But obviously, it is, from the practical point of view, this is completely garbage, because this does not represent this circuit with a 10 kilovolt input signal. So let's now go back to this original circuit and make it compatible with the requirements. And I'm now going to put here 10 millivolts and 20 millivolts rather than 10 volts and 20 volts. I'm sort of altering the problem. And in this case, if you do the calculation, you'll get 40 millivolts. This is what SPICE will show you, this we know, but in this case, you see that you get a very nice sinusoidal waveform, because small signals are sort of additive, and you get this small signal AC, the amplitude of which is 40 millivolts. Here it is. This is from 2, the reason it's 2, because the DC is added to it, and then we have superimposed only the AC component, which we see here, which has the 40 millivolt amplitude. So everything is fine here. So let me finish up with another example, just for illustration. And here we have an amplifier with a BJT transistor. It has a 15 volt supply, some resistors, and it is fed from a 20 millivolt. Very careful now. It's a small signal, and so it's within the values of the DC, coupled with the 1 microfarad capacitor, and I run it in AC analysis. And this is what I'm getting. Is this correct? Well, yes and no. It is correct in the sense that this is the output that you'll get here. But it has nothing to do with an amplifier, because if we consider the voltage divider here, it turns out without the loading of the transistor, the voltage here is 0.15 volt, insufficient to turn on the base to emitter junction. So this transistor is in cutoff. The voltage here, since there is no current, there will be 15 volts. And what we see, in fact, is the penetration of this signal through this capacitance between collector and base. And it makes perfect sense. At low frequency, penetration is low. At high frequency, the capacitor is sort of a short, and you get all the signal out. This is a 20 millivolt, you get the 20 millivolt out. So the point is that although the circuit is really represented by the small signal, and it's being analyzed, and the solution is correct, but this is not what you probably, or what the designer probably intended, because it might have a error in one of the resistor, and therefore one has to be extremely careful that the operating point is indeed correct, such that the linearization is around the correct operating point and not some obscure point that has nothing to do with the intention of the design. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and that it might be useful to you in the future. Thank you.